Okay, welcome everybody. Today we're taking a closer look at the Boyle's Law practice problems. And you should be at a spot where if I said, what's Boyle's Law, you understand that Boyle's Law is the inverse relationship between pressure and volume. So I'm not going to tell you that that's the only way you could define Boyle's Law, but there's a few things here that I want you to understand. If we're working with pressure and volume, all right, that means temp or temperature is our constant. So we're going to assume that temperature is like held in check. And then we're going to take a look at what happens with pressure and volume. And what we'll always see is that it's an inverse relationship. And that's a fancy way for saying opposite. So in Gay-Lussac's law and in Charles' law, we had proportional relationships. For Boyle's law, if we were to graph out some data, what we'd find is if we've got pressure here on our y and volume here on our x, if you've got a lot of pressure, high amount of pressure, it's going to be squished down into a low volume. And if you have a low pressure, then you're going to have a larger volume, which is really just kind of like saying if you've got a lot of squish down on something, your pressure, it's going to squish it down into a smaller space. So the way I always kind of use the examples from the lecture videos to keep you in check with this is that balloon that they put in the vacuum chamber. And you might remember that they put the balloon in the vacuum chamber and they pulled all the air out. So there was no pressure and the balloon got real big. And then they pumped the air back into the vacuum chamber and it got squished down and it got smaller. So a real quick review here with pressure. The one-word definition that I always use for pressure is push. We're going to think of that as like some push. And our one-word definition here for volume is going to be space. And temperatures are constant here, so we're not really going to fiddle with that much, but I want you to think of temp as your one-word definition of movement. So when we say something's hot, it really just means that it's moving fast. So if I've got these guys here, say this is my sealed container or whatever, and I've got some gases that are zipping around, every time they collide in with this wall, there's going to be some push. And what we're going to see here is if you've got an outside push, that can kind of change things a bit. So enough of that. We'll get back to that a little bit later. Our formula here, it's the only one where I guess it looks different. You're going to be multiplying. And I've got P1 times V1 equals P2 times V2. With this formula, remember when we have the 1 or the 2 in subscript, that's really just a way of saying, hey, these are the starting conditions for pressure and volume, and these are the ending conditions for pressure and volume. And I'd encourage you to, even before you try to solve any of these problems, just writing out P1, V1, P2, V2. And as you read through the problem or you pull out the information, you're organizing it. And it is important that you put a pressure in the right spot or a volume in the right spot because these guys are linked. These are like the starting conditions, the ones. And what the pressure and volume of the gas is like when it's all said and done, those are linked. That's your ending there. We've got some other little clues for what would have to go where. If I jump back to our one-word definitions here with, again, pressure being push and volume being space, it's good for us to go through the units. There's actually a lot of different ways that you could measure pressure, but for all of Unit 3 for Chem B, we're going to go with ATM, which is the abbreviation for atmospheres. And like we'd mentioned before, 1 atmosphere is just like 1 atmosphere, Earth atmosphere pressing down, and that's what we use for that. And for our volume, we're going to use liters. Okay, so I've got my preset up here, right? I haven't even read through a problem yet. Let's take a look at example 1. And I'll usually read through the whole problem first. If we took 2 liters of gas at 1 atmosphere and compressed it, it's a fancy word for saying squished it down, to a pressure of 2 atmospheres, what would the volume of that gas be? So before I even plug in any numbers, I'm just kind of thinking here. I know pressure and volume and Boyle's law, that's an inverse relationship. So that means the opposite's going to happen. So if I had 2 liters of gas at 1 atmosphere of pressure, and this is saying that I squished 2 atmospheres of push or 2 atmospheres of pressure there, what do I kind of think would happen to the volume? So if the pressure went up, if this was squishing that container down more, do I expect the volume to get bigger or smaller? If I've got more push on it or more squish on it, is that going to make it bigger or smaller? Think about if I had a balloon, I press down on it more, I think I'm going to find that my answer should be smaller. But let's go through and run the calculations. All right, so here's my starting conditions, right? I got 2 liters. I know that this has to be volume because volume is measured in liters. I got 1 atmosphere. Okay, so this doesn't just come right out and say the pressure was 1 atmosphere, but that makes sense. I mean, we measure pressure in atmospheres. So I got 1 atmosphere. Then the ending spot here, this does say pressure of 2 atmospheres. If it just said we compressed it to 2 atmospheres, I need to know that atmospheres has to be with pressure. So then that would be here. We're looking for volume. I'm just going to call that X. So now I don't even really need to look at that sentence anymore, right? I can just organize things. Using this formula, I can match or plug things in, right? So there's my P1 times my V1 equals my P2 times my V2. Let's see here, I got 1 atmosphere, 1, 2 for my volume. Here I had 2 atmospheres and my volume was X. So what do I got to do? Solve for this X over here, right? So on this side, 1 times 2 is 2. Here I had 2X. I got to get X by its lonesome. So I'm going to divide by 2 here. That gives me X. Since I divided by 2 here, I have to divide by 2 there. Without even reaching for a calculator here, I can tell you 2 divided by 2 is 1. So what was I looking for? I was looking for that ending volume, right? So that means that my unit for this has to be 1 liter. And if you're kind of thinking this through, and you were thinking, well, yeah, the pressure went up, it's an inverse relationship, the volume should go down. There was more press on the outside of this can, more push on the outside of this, right? So I would expect it to get squished down, just like that balloon in the vacuum chamber. And if you take a look at this as well, 1, 2, 2, 1. If we doubled the push, or we doubled the atmospheres, it kind of makes sense that we halved, or, cut in half the overall space there. So say I'm losing you here, or you're just not thinking it through that way, but you're like, I think I did it right, but how on earth could I double check this, Cash? Well, check this out. If you're going to say this is your 1 liter, right? Boop. So if I've got P1 times V1 equals P2 times V2, and then I go through and I say, all right, well, I started off with 1 atmosphere at 2 liters, and it should be equal to my ending stuff where I doubled the pressure to 2 atmospheres, and I just calculated that it was 1 liter. Well, check this out. 1 times 2 is 2. 2 times 1 is 2. Bingo, bango, bango. Everything worked out. So you can actually double check these before, a quiz or whatever, and check to see if you're right. Or, if you're feeling confident, I guess that's an option as well. As always, you got questions or concerns, please feel free to ask me in class or shoot me an email. Bye-bye.